Hello, my name is Marcus Hamilton and I'm a senior software engineer at Eclypses Incorporated within the Colorado Springs technical team. Eclypses has a disrupting cyber technology offering organizations an advanced data security solution not seen in today's environments called MTE Technology. Eclypses was founded with the primary focus of developing the MTE technology to be the most innovative and disruptive data security solution for mobile application technologies, websites, and IoT devices. The development of this technology led to the MTE Toolkit as we know it today. But we wanted to demonstrate that MTE technology can fit even into one of the smallest gadgets we know today, a car key fob. The key fob, a simple remote control that enables you to lock and unlock your car. Its technology is one of the primary target of car thieves. In this video, I will show you a working key fob built using standard electronic parts, which utilizes our MTE technology. The MTE data this key fob sends out can only be interpreted by the vehicle it is paired with and cannot be manipulated while in transit. There is only one MTE data value that is valid for a given command, and that value is instantly obsolete once used, meaning it will never be valid at any other time. These important characteristics of MTE eliminate the vulnerabilities of current key fobs, including man-in-the-middle attacks, replay and delay attacks, rolling PWN attacks, etc. So let me try to explain MTE really quick by talking about two-factor authentication, which is a somewhat similar concept. When I log into my bank account, I basically tell my bank who I am. The bank generates a PIN number and sends that number to my cell phone, and I type that number into a form on my bank's website. After that, the bank knows that I am the authorized person. Let's think about that for a minute. The information which is transmitted by the PIN number is always the same. It confirms my identity. But the PIN number is different every time I log in. The PIN number becomes obsolete the very moment it is used. MTE has a similar concept. Information is replaced by random data, which becomes obsolete the moment it is used. The same information looks different every time it is encoded using MTE. But MTE is much more advanced because we do not need to send the PIN number from the car to the key fob just to send it back. The key fob knows how to create that next number. And this is our key fob development system. It is a development system, which means this little computer board can be used to create prototypes for many different applications. But look at the green circle. This circle shows you which parts of this development board would be present in a production key fob. And look at the quarter coin next to that green circle. You can imagine how easy it will be to build a production version of this key fob. The microcontroller we're using here is from Microchip and is based on a MIPS 32-bit processor core. MIPS processors are often used in home internet routers, but this one here runs at only 8 MHz. It has 8 kilobytes of RAM and 64 kilobytes of flash ROM. Kilobytes, not gigabytes. Any standard smartphone these days probably has 2 gigabytes of RAM, 64 gigabytes of flash ROM, and runs at peak clocks of up to 2 gigahertz. But our little key fob is supposed to be powered by a coin battery like a CR2032. Our key fob has 2 buttons, one for lock and one for unlock. The lock and unlock commands are transmitted by this little module here, which is a very simple 433 MHz AM transmitter, the very same technology used in garage door openers. This transmitter sends out information bit by bit at a rate of 2000 bits per second. This little transmitter is a module made for hobbyists. It will be much smaller in a production build. On the receiver side, we would have the car, but since having a car in my office is not practical, I decided to simulate the car using my Android tablet. So here we have our receiver setup. This receiver board itself does not have anything to do with MTE. It is a little Arduino microcontroller that is connected to the 433 MHz AM receiver module. It reads the incoming bit stream from the receiver module and sends this data over the USB to an app on the tablet. That app simulates our car. In a real car, the receiver would be the BCM, the body control module, which is a computer that controls many features of a modern car, like lights, door and hatch locks, windshield wipers, air conditioning systems, immobilizers, etc. This app, our car simulator, shows the lock status of the doors, the trunk lid and the windows. This car simulator has the following features. When the doors are locked and it receives an unlock command, the driver's door unlocks. When it receives an unlock command and the driver's door is already unlocked, all doors are unlocked. When it receives a long press unlock command and the doors are unlocked, the driver's door window will roll down. When it receives a double press unlock command and the doors are unlocked, the trunk lid will unlock. When it receives a lock command and anything is unlocked, all doors are locked, the trunk lid locks, and the windows are rolled up. When it receives a lock command and everything is locked, it honks the horn to help you locate the car. These features, of course, could vary among makes and models. We could also have more than 2 buttons on the key fob. All that does not matter. The one thing our key fob has in common with other key fobs, it needs to be paired with its receiver. This process is usually done in the factory when the car ships to the dealership, or at the dealership when the key fob is replaced or added. It is very similar to the learning process of your garage door opener. The receiver, which is our car, is placed in a special learning mode where it will accept the credentials of a key fob. The key fob transmits these credentials when a certain combination of button presses is executed. The transmission of the credentials is acceptably safe because the transmission range of the key fob is in the range of 100 to maybe 200 feet. Even if someone can listen in on that pairing transmission, it does not mean that someone can understand the transmission. And keep in mind, this pairing process will probably never have to be redone. The pairing credentials are unique to each and every key fob. They also will never repeat. Once the car has received the key fob's credentials, it is in sync with the key fob. In this environment, we have full knowledge of the transmission path. It is directly over the air with no service network in between. And MTE makes sure that we use zero trust. MTE will always verify that a command received is valid and originates from a verified transmitter. Let's see how this system works. On the left-hand side, you can see a text terminal which I have attached to the key fob transmitter board. This terminal helps us to see what the key fob is doing, and it also shows the actual data being transmitted. On the right-hand side, we can see the Android app which simulates the car. Just under the graphics showing the car, there's a little terminal-style window that allows us to see what the car app is receiving and how it is interpreted. We start this demonstration with the status of everything's locked. I now press the unlock button on the key fob. On the left-hand terminal, we can see that the key fob recognized an unlock button press. The driver's door is unlocked. We can also see the actual data which is being transmitted, a series of 12 bytes of random data which is shown in hexadecimal notation. This is the data generated by MTE and it means unlock. On the right-hand side, we see that the car received this exact series of 12 bytes and MTE decoded the meaning as unlock, so the driver's door is now unlocked. Let's try again. The next unlock will unlock all doors. I'm pressing the button. But look at the transmitted and received data. They match, of course, but they are totally different from the unlock we just sent a minute ago. That is MTE technology in action, unpredictable and not reproducible. If I would change the software in this key fob so that it cheats and would send the same data for unlocking twice, it would not work the second time. Man in the middle and replay attacks become useless. This is the best security you can get for a key fob and the car attached to it. But let's keep going. I'll do a press and hold on the unlock button now. Since all doors are already unlocked, the car simulator will roll down the driver's window. All the information that the key fob sent was unlock and then hold unlock 2 seconds later. And again, after being protected by MTE, these very same unlock commands look totally different. Let's lock the doors. I'll press the lock button. As we can see, everything is locked again. We are back to the initial state. And another lock helps us to locate the car in the parking lot. The car honked the horn. And of course, This lock looks completely different than the one we just did before this one. Let me put out a few technical details about this key fob. The complete software in this key fob has a size of about 23 kilobytes. Not just MTE, everything. The whole application. It uses a bit less than 4 kilobytes of RAM. The processor is a MIPS 32 core running at 8 MHz, but at the current data rate of 2000 bits per second of the 433 MHz transmitter, it takes about 100 milliseconds to transmit a command over the air, and it takes MTE not much more to encode the data. In less than half a second after the beginning of a button press, the receiver knows what to do. And we are bringing MTE down to the 16-bit microcontrollers and even the well-known 8-bit AVR microcontrollers from Atmel. No device is too small for MTE. Just think about the possibilities. Surveillance cameras, security systems in general, access control systems, card payment processing terminals, industrial monitoring like pipeline pumps, remote control of power stations, automotive applications like secured communications between engine, transmission, and body controllers. The possibilities and necessities to secure communications are endless. And all these systems contain embedded systems and microcontrollers. They all transport sensitive information. MTE can secure just about any communication on any transport medium under the control of any soft or hardware protocol. My colleagues and I, the engineers at Eclypses, hope that this little demonstration was useful to help you understand the vulnerabilities of embedded systems and IoT devices, and how MTE can help you secure your communications to build better, safer, and more successful products. I want to thank you for your time watching this video. If you would like more information on our MTE technology, please visit eclypses.com or email contact@eclypses.com to set up an exploratory meeting on how Eclypses can help you reach your security goals.